So great, we know how to take a priority queue and represent it as a heap. But how do we represent a heap in Java? So this is actually a deeper question we're going to talk about, which is how do we represent trees, period, in Java? And so let's discuss some different approaches. So the first approach is one that's going to seem incredibly natural. In fact, it's going to seem like there's no other way. This is approach 1A. In this approach, whenever you declare a tree, well, you set up some kind of key, maybe also a value if you're doing a map, and then a set of nodes or pointers that are going to go to other trees, right? You've done this before. This is how you implemented BSTmap. In this case, it happens to be a trinary tree instead of a binary tree, but it is basically the thing you think of as a tree. But there's actually other ways we can do this. So here's an approach I'm going to give, which is very similar. It's still going to create a mapping from each node to its children, and this next approach will be called 1B. So in this approach, what we could do is in each tree node, we could have, well, the key, as we had before, but then now an array of child links. So it's kind of a hybrid approach, where instead of just strictly having only variables, where each variable represents a link, now the variable can be an array of links. And so, for example, if we have here the tree W, X, Y, Z, which before we represented in this very obvious way, where W has a left pointer to this node, a middle pointer to this node, and a right pointer to this node, now what happens is, well, each of these tree nodes consists of a key and a link to an array. And that array holds all the children, in this case, X, Y, and Z. And each of these will have their own link to their own array, and in this case, you can support variable width nodes. So it's a more general approach, and I'm not going to say that one way is better than the other, but I will say that this approach, the reason you've been using it is because we've been using, in the past, mostly strictly binary trees. And in that case, we want to keep things simple, but if you needed to support something more complicated, it might look something like this. Now there's another rather strange approach, which I'll show you now. So this next approach is going to be, again, representing the tree where W is the root, X is the left, Y is the middle, and Z is the right child. But here, the way we would actually store it in Java, well, here W keeps track of its child X, and then, interestingly, X keeps track of, well, it's what you might call, I don't know, sibling, right? So X knows its sibling Y, and Y knows its sibling Z, and W is only going to keep pointer to one of its most favored children, right? So it picks favorites. So you might call this thing a sibling tree, and in this case, tree 1C, we point at our favorite child, the one we love the most, and we let him take charge of the siblings because, we don't want to think about all these kids. Okay, so this is another way we could do a tree. And I'm bringing these up not because we're going to use these for a heap, but because I want to make it clear that there are many possible approaches to representing a tree, and there's still yet more crazy ideas you could have, but we're going to take a little bit of a left turn now and talk a lot about how we can avoid having pointers at all, how we can use only arrays, okay? And that's ultimately going to lead us to how we'll usually represent a heap. So these are our linked data structure style trees. This one's a little bit of a hybrid since it has an array involved in the whole process, but fundamentally these are all linked data structures. And so in this other type of approach, approach 2, we'll store our keys in an array. And we'll also store the parent IDs in an array. And this is similar to what we did with the disjointSets data structure. Okay? So for example, if we want to represent the tree W, X, Y, Z, we might store the key identities. So we'll say key 0 is W, key 1 is X, key 2 is Y, key 3 is Z. And then we'll say that, well, your parents are, this is parent is W, 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 and W is its own parents, like disjointSets. Now obviously this is a very boring example, so I've created a larger example here that hopefully will make it a little more clear what's going on. And in this example, what we see is we have two arrays. This is all of the keys, K, E, V, B, G, P, Y, etc. And here I have my parent links. So 0's parent is 0, 1 and 2 have parent 0, 3 and 4, they have parent 1, 5 and 6, they have parent 2, 7 and 8, they have parent 3, 9 and 10 have parent 4, 11 and 12, parent 5, and 13 has parent 6. Okay? This is a lot like what we did with disjointSets. And this is a tree, right? Anything, you could in principle write operations that do things like find minimum item or rotation operations or whatever, right? This is a valid way to represent a tree using an array. One of the most important things, of course, in computer science is managing complexity, layers of abstraction. So here I'm just saying that one interesting abstraction, one way to represent a tree is as two parallel arrays. Okay. And I'm actually going to notice something very interesting. This tree, right? Is it complete? Think about that. Yeah, it's complete. And so something funny will happen. If you're trying to represent an approach number 2 tree that is complete, you will always get this pattern. 0, 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. Okay? So approach 3 is going to be an interesting approach where we assume the tree is complete, and we'll just ignore that array. So approach 3 is the following. We just get rid of that array. So it's just the same as approach 2, but cut it out. And to interpret this array, what we're going to do is just assume the tree is complete, and obviously this approach is only going to allow us to store complete trees. Okay? So this is a hyper-specialized representation of a tree. It only works for complete trees. And in this case, if we want to know that it's, and in this case, we're assuming that down here that it's a binary tree. Up here, that it's a trinary tree. So you have to know what kind of tree you're getting, but essentially here what we're doing is this data structure, right? It's just about the most compact thing you can imagine. Okay. Now it turns out that because heaps are always complete, this is the typical implementation that people will use for a heap. Okay? And we'll come back to this in a moment. So to summarize all of the tree representations, right? There are many ways of representing trees. We have these 3 which involve linked data structures, and then these 2 approaches, approach 2, where we have an array of keys and an array that represents the structure, and then finally approach 3 where we only have an array of keys, and in this case we're assuming that the structure is a complete tree. Okay. So now let's talk a little bit about heaps. And before I get there, I'm going to introduce actually yet another tree representation, but it's only a very minor tweak on approach 3. This is approach 3b. In approach 3b, it is exactly the same thing as approach 3, except we're going to move everything over by 1 spot and leave a blank at the front. Now why? Why on earth would we possibly do that? Well, it just makes calculation of children nicer. So recall that one thing you want to do with a tree often is, I want to get my left child. And so with a data structure like this, it's obvious. All you do is you say dot left, right? But when you have a tree that is based on arrays, you have to actually do some kind of computation. And so if we leave an empty spot at the front, it is nice because if I want to know somebody's left child, I just multiply the index by 2. So for example, 5's left child is 10, right? Here it is. So I just take 5 and multiply by 2. You can see that works anywhere, right? And likewise, the right child will just be the number multiplied by 2 plus 1. Okay? So yeah, you can do a array-based tree with approach 3 without this empty spot, but our book, the optional textbook for the class, uses this approach, and in the lab after spring break, you'll implement a minimum PQ, which is based on this data structure. Okay? So that's one way we can represent trees, and in particular here, complete trees. Okay? So if you wanted to implement a priority queue using a heap, well, you have to implement the heap somehow. And if you implement the heap using approach 3b, where we store a tree like this, okay, let's think about all of the runtimes. So how do you add to an array-based heap implementation of a priority queue? Okay. Well, if I add, what that means is I'm going to go to the end of the array and I'm going to add a new item, and then I'm going to swim up the tree. So if I insert here, then I know my own ID, so I can divide by 2 to get my parent, divide by 2 to get that parent, divide by 2 to get that parent. And so ultimately, all of those array accesses, climbing the tree each time I need to look somebody up, it's actually going to be quite fast. Oh, sorry, it's going to be quite fast. It's going to be log n. Because my tree is complete, and calculating my parent is complete, so, calculating my parent is constant time, so I'm just going to climb the tree one little bit at a time until I get to the top. How about get smallest? Well, that's going to be time 1, constant time, because I just need to return item 1 in the tree. And then how about remove smallest? Well, in that case, what I'm going to do is take the last item from the array, put it in the first position, and then sync it. And so I'm going to do 2 comparisons to my left and my right child, and sync my way all the way down the tree. And I'm not really doing a detailed analysis. I'm kind of just doing it out loud, because I think this is something you'll appreciate more when you do study guide questions. But in this case, calculating my children is very fast, accessing my children is very fast, so will also be log n. Now I'm going to make a note here, which is that my heap is actually log n time amortized. Okay, why is that? Well, of course, an array only has a certain size, and so once it gets too big, I'm going to have to resize it just the same as we had to do with array dex. But yeah, those resizes aren't going to be such a big deal. So the punchline is that a heap has these nice logarithmic time operations, and yeah, they're amortized time because we need to maybe resize my array up or down, but they're quite fast. Okay. Other notes, well, another is that's very important. Another advantage of a heap, other than its simple implementation, is that it handles duplicate priorities much more naturally than BSTs. So if you have objects which have the same priority, a bushy BST is not going to naturally handle that, one of the main reasons we want a heap. And then finally, I'll mention that an array-based heap will generally take a lot less memory compared to a tree-based heap, something like representation 1a. So if you're using approach 3 versus approach 1a, you expect to save about a third, or usually about a third of the memory. Now, it's a little beyond the scope of our class, but if you're very curious, there'll be an A-level study guide question for you to check out. So the last little thing I want to talk about, because eventually you're going to implement this in Java, is just to remind you or to look back at our Java interface and see what's missing. Okay? So of course, we have this question, which is we need to make sure we can order items. Every item needs to make sure that, in a minimum priority queue at least, that it is smaller than all of its items below. And so this interface, we'll notice, does not guarantee that items are comparable. Okay, so what's missing? Well, we are missing something like item extends comparable. Another question you might ask is, let's suppose we don't want to necessarily use the natural order for items, or maybe we don't want to only allow comparables. How could we change things? Okay. Well, one thing we could do is create a constructor for a particular priority queue that accepts a comparator, so that whenever you create a priority queue, it has a comparator in mind that it's going to use to order items, something like that. So that's more or less the whole story. Yes, there are also maximum-oriented priority queues, but they're almost basically the same thing as a minimum-oriented priority queue, so I'm not really going to talk about them. But I think that this is a really great example. This whole priority queues are implemented by heaps. Heaps are implemented by arrays. Of the notion of how we can have these layers of abstraction that will ultimately lead to something that is beautiful, efficient, and not that hard to code out. So that's it on priority queues.